and welcome. Myself, Professor Vikash Katariya. In the last lecture, we had discussed the 5-state process model, in which we have discussed different 5 states of process. There are new, ready, running, terminated, and waiting. Right? But if we talk about the Unix file system or a Unix, that is the multi-user operating system, it has the different structure of process, and the process life cycle contain number of states. There are 9 process states model. So let's have a look the Unix process states diagram. So in this lecture we are going to cover the topic which is based on Unix process state diagram. Right, so let's have a look. We have different kind of states. First, it indicates the user running process. Process is starting from the step first, then the step 2, that means kernel running states. Step 3, that is ready to run or memory. Step 4, maybe a slip in memory. Step 5, ready to run or swapped. Step 6, slipped or swapped. 7, preempted process. 8th, not enough memory. In that case the process may be swapped out. Again it will created by the fork system call. And the 9th state, that is zombie state, at the end of condition, at the end of process, after exiting or terminating the process, it becomes the zombie state. Okay, so how the single process comes in various states, how the life cycle of Unix process states comes into the picture, we will discuss one by one in step by step. Right, so process states and transition. The lifetime of a process can be conceptually divided into a set of states that describe the process. The following list contains the complete set of process states. So let me start with the first step. The process is executing in user mode. The process is start our execution in user mode. Let me tell you about the user mode. So whenever you create a new program, you need a editor. You type vi space the name of programs which you want to be part of process. So anytime if you're working with a vi editor, that means you are creating your own user area. Okay, so the process is starts from the user mode or user area. Every user identified by the every user identified by its U area, and every user identified by its ID, which is known as UID. So user has its own U area and user has its own ID, which is known as UID. Right, the new process always creates with the fork system call. So user creates a new process via calling a fork system call. Okay, now then step 2, the process is executing in kernel mode, that is the kernel mode. Let me tell you about the kernel mode. Everything is not possible into the user area, because there the execution of system calls, the code of system calls, the code of built-in functions. So how the code will work, how the function will work, that is not known by the user. So anytime if user suppose call the printf function, scanf function, the detail of printf function, that is the part of kernel. It is the subject of kernel, right? So in that case, the process switched from user area to kernel area for executing that particular area of the program or a process, right? Because the code of printf function, the code of scanf function, getch, any function which is built in may be used by the user in our program. So executing that particular area of a program or a process, the process switched our context from u area to kernel area via interrupting. That's why here system call interrupted, because user wants to execute their entire program in the built-in library functions, so it has to require kernel for executing that. So the process switched from state 1 to state 2, that is kernel running area. I hope you clear. So process came kernel area because it wants to execute the system calls, right? In the step 2, the process is executing in kernel mode. Okay. Step 3, the process is not executing in step 3. Process is not executing but is ready to run as soon as the kernel schedule it. Okay, there may be chance if process switched from process 1 user area to kernel area and CPU is not ready to execute at that time. So process forward this process to step 7 printed, and the process 7 return to the user area, and user area again it will return the step 2. Okay, so it will move like that, 1 to 2 to 7, 7 to 1, 1 to 2 again. Okay, so the process is not executing but it is ready to run as soon as the kernel schedule it. Okay, so step 3, the process is not executing due to some reason but ready to run as soon as kernel free or schedules it. Right, now the step 4, the process is sleeping. Now you can see here, at the time of execution of the process in the step 2, that is the kernel running mode, process may require some input output operations, process may require some interrupt, means some hardwares. At any case, if it required something and being this requirement the process gets not terminated successfully, it may be go on sleep mode. So from step 2 it moves on step 4. So process is sleeping and resides in main memory in that case, right? So step 4, the process is sleeping and resides in main memory due to any requirements of input output operations, right? That is why it goes to the memory, otherwise it could be terminated successfully. So after the end of execution the process goes on zombie state, death state, right? But it will not. If any interrupt comes into the running state, it sleep from state 2 to step 4. It moves to step 4 to step 5 because we need to swap out the process from memory. Asleep in memory, that means sleep, swapped out. So 4 to 6. So the 5 state, the process is ready to run, but the swapper must swap the process into main memory before the kernel can schedule it to execute. So there may be a swapper which works in between the step 3 and 5. 3, 4, 5, 6. In between there are swapper which take care about the swapped process. So let me write here the process ready to run, but swapper program must swap the process into main memory before the kernel can schedule it to execute. Okay, so after 2 it goes on step 4, asleep, then sleep, swapped, 4 to 6, 6 to wake up call for step 5, ready to run, swapped out. There may be chance if there is no enough memory, then it will also stored onto the hard disk. In step 3, swap in, swap out. So ready to run process, but it will swap in as per the requirement of kernel. If kernel notify to the process 3, step 3, 3 will swap in the process which is stored in somewhere into the memory location. Okay, and again the process goes on step 2, that means kernel running mode. So this is about step 3, 4, 5, 6. The swapper process works in between step 4, 3, 4, 5, 6. Okay, step 5, so step 5, let me write here what kind of process we need to do. In step 5, the process is ready to run. As you can see here in the step 5, process is ready to run states, but we need to swapped in from 5 to 3. So let's do it. The process is ready to run, but swapper program, sorry, we have written again. We already written in the step 5. Let's have discuss on step 6. As you can see, the step 6 process is in sleeping states, and the swapper has swapped the process to the secondary memory to make room for other processes in the main memory. Okay, so process, if process exists in the step 6, state 6, that means the process is permanently swapped out from the primary memory and it is situated at hard disk. Okay, and via wake up call it will be resumed into the primary memory. So step 6, the process is sleeping and the swapper has swapped the process to hard disk to make room or space for other processes in main memory. Okay, this is about the step 6. In the step 7, as you can see here, the process is returning from the kernel to user mode. The process returning from the user mode to kernel mode, from the kernel mode to user mode, because as I told you that at the time of execution there may be chance the higher priority process maybe comes from the user mode to kernel mode. In that case, the kernel in which the process is running or executing, at the same time the executed process must be swept or preempted by other process. Okay, suppose the lower priority process is executing in the kernel running mode, but if the higher priority process comes into the kernel mode, that running process may be swept out. So the process which contain the higher priority preempt to the next process which contain the lower priority. So lower priority process preempted from step 2 to 7, and it will store to the step 7. Then it will again resume by the user area. So that is why the arrow is looking like that, from step 7 to step 1. So preempted, that means we are pinging something. Okay, we are swapping, we are taking away this process from kernel area to somewhere else. This is called preempted. Okay, so step 7, the process is returning from kernel to user area, but the kernel preempt it and does a context switch to schedule another process. So let me clear here word preempts. It stands for CPU can preempt to lower process if higher priority process comes into kernel area. This is called preempt. Okay, second is non-preempt. It stands that CPU never swap currently executing process. Non-preempt means CPU never swap out currently executing process from kernel to user area. It will swap after the end of execution. It will swap out after the end of execution, right? So in between the execution, CPU never leave that process. This is called non-preempt. Okay, so in step 7 there is concept of preemption and non-preemption. In the step 8, as you can see here, the process is newly created. In the step 8, the process is newly created using the fork system call and is in the transition state. The process exists but it is not ready to run, nor it is sleeping. So it is created but it is not ready to run states. and not in sleeping state, so it will take some time in user area. This state in the start states for all processes except process 0. So the Unix structure start from the process states 8, where the fork system call and create a new process. If it is enough memory, then it will store into the primary memory, switch from the kernel area if it required. Maybe it will swept on user area if typing work is remaining. Okay, maybe print into the printed area and again rescheduled by the user area. Okay, and so on. So step 8, the process is newly created and is in a transition state. The process exists but it is not ready to run, nor is sleeping. This state is the start state for all processes except process 0. So this is actually the Unix system structure. I hope you clear. Step 1, 2, 3, 4, 5, 6, 7, 8, 9. Every state have their own meaning, have their own concept. Okay, so the life cycle of Unix process may contain 9 different states. So start from the 8, where the new process created, and where the new process creates by the user, and it will move in certain different area, a different location and different states, and at the end of execution it stored into the zombie state. Not exactly stored, the end state of the process is known as zombie state, right? So that was the topic. Thank you.